In this chapter, we're going to take a ride down the graphics pipeline. I want to give you a tour of what happens inside the graphics chip so that you can see where the shader that you'll write will fit into the chain, and so that you'll know what happens to the graphics data before and after your shader. So to get started, we're going to be on the CPU. And generally what happens is you're running a 3D program like 3ds Max or a game, and that 3D program sends 3D instructions to Direct3D or OpenGL, and Direct3D takes the instructions from the 3D program and passes them from the main system processor, the CPU, across onto the GPU, the graphics chip. The graphics chip receives these in an area of the chip called the GPU front end, which is a special piece of hardware designed for communicating with the central processing unit, the main processor. At this point, the data that's being passed to the GPU is in the form of vertices, and that vertex data gets passed to the programmable vertex processor. So here we have 3 vertices, a red vert, blue vert, and a green vert, and these vertices at the programmable vertex processor are transformed. And what that means is when the vertices come in from the 3D program, they're in object space, which means their positions are all relative to the center of the object that they belong to. And in order to get placed on the screen, the verts need to be placed relative to their positions on the screen. So that happens right here in the programmable vertex processor. The other cool thing that happens right here is the vertex shader. And the vertex shader is the part that you write. Vertex shaders can manipulate any of the information that came in from the CPU. It can move verts around, adjust the color of the verts, or tweak the vert normals, for example. In the past, when graphics hardware wasn't as powerful, the vertex processor did most of the work. Increasingly, the vertex processor is simply being used to prepare the data for the pixel shader, and most of the magic happens in the pixel shader further down the pipeline. We'll get to that in a second. So the next thing that happens is primitive assembly. And what that means basically is connect the dots. So the programmable vertex processor passes the vertices to primitive assembly, and primitive assembler connects them to create triangles. So you've just got vertices at this point. Once they're passed to the primitive assembly, you get triangles out. The primitive assembler passes the triangles to the rasterization and interpolation unit. And what happens here is all the triangles are cut up into screen space pixels. So instead of just having a triangle here, now we've got a set of pixels that represent that triangle. This step is a little bit like taking something from Illustrator into Photoshop, where in Illustrator we're talking about lines and points, and in Photoshop we're talking about individual pixels. So the rasterization and interpolation unit on the graphics chip is doing that automatically. Basically, it's taking the triangles, converting them into pixels. And also, during the rasterization and interpolation step, we're interpolating the vertex data to the pixels. And what interpolation means is, for example, we've got a blue vert here and a green vert here. So all of these pixels in between need to be somewhere in between blue and green, and that's what we can see happening here. So on this side, near the blue vertex, we've got blue pixels, and as we move closer to the green vertex, we've got green pixels. Same with the red. Now this happens to all of the data. So for example, if this blue vertex has a normal that's pointing this way, and the green vertex has a normal that's pointing this way, each of the pixels along the way will have a normal that's somewhere in between here and here. The normals are interpolated across the triangle, so each pixel gets its own normal that's partway in between. Same thing works with UV coordinates. Say this blue vertex has a UV value of 0, and this green vertex has a UV value of 1. All of the pixels across the triangle will be somewhere in between 0 and 1. So all the data that's contained in each vertex gets interpolated from one vertex to the next, right here in the rasterization and interpolation stage. Next, that interpolated pixel data is sent to the programmable pixel processor. The pixel shader that you write can take the data here in the programmable pixel processor that's been processed in the vertex shader and data from the CPU to determine the final color of the pixel. When we talk about passing data from the vertex shader into the pixel shader, this is the process that we're talking about. The data comes out of the vertex shader, gets interpolated from each vert across the triangle, and then goes into the pixel shader as pixel data, where the pixel shader can use it to determine the final color of the pixel. After the pixel shader runs here at the programmable pixel processor, the data is sent out to another unit where some final raster operations are performed, and then the pixels are sent to the frame buffer where they wait to be added to the screen. So there you have it, a tour of the graphics pipeline. And the main thing that I want you to see from this tour is that when you write a shader, you're writing two different pieces of code. You're writing a vertex shader that runs here at the programmable vertex processor, and the vertex shader works at the vert level. It's only doing things to the vertices. You're also writing a pixel shader that runs here at the programmable pixel processor. The pixel shader works at the pixel level. So you have control over both vertices and pixels. And what's really neat about that is you can decide while you're writing your shader exactly where you want each piece of information to be processed. For example, if you're writing a simple shader, you can do your lighting processing over here in the vertex shader. But if you want something more complex or a little bit more fancy looking, you can do the lighting here per pixel. And what that means is that your shader will be a little more expensive because it's doing all these instructions for every pixel instead of just for every vertex. But it also means it's going to look a lot nicer. So I hope this tour that we've taken has given you a better idea of exactly what happens to the data once it gets passed into the GPU and how the shaders that you'll write will fit into that chain. In the next chapter, we're going to be talking about setup. I'm going to explain what program we use for writing shaders, what program we use for viewing shaders, and how to get both of them set up so that they'll work and so we can start writing our own shaders right away.